Welcome to physics lesson 6.05 on centripetal force. So we left off last time talking about centripetal acceleration, and we said if we have a circle, let's see if we can draw a decent circle this time. Not much better. Oh, art. And we had a roulette ball that was going around our circle. We said that this roulette ball had a tangential velocity that left tangent to the circle, and it had centripetal acceleration, an acceleration that points to the center of the circle. And even if this is moving at a constant speed around the circle, it's changing its direction. And so that means that there has to be acceleration there. Well, here's the thing. If there's acceleration, there is also force. So we also have to have centripetal force. And we said that the implication so let me grab. So we said our implication last time was that objects want to move in a straight line. Objects move in a straight line unless they're acted upon by a force. Unless they're acted upon by a force. So centripetal force is what we call this force centripetal force. Or F sub C. Now, you might think we're introducing a new force, but actually we are not. This is not a new force. So let's go to another example. Let's say I'm going to try to draw again. I know it's painful. Sorry about that. Let's draw a U swinging on a rope over your head in a circle, a ball. So I'm going to put a ball on the end of our rope. And we're going to indicate that that's going in a circle. Let's see if I can make my circles any better. Now, I can't really draw it with a bird's eye view, but if you were drawing bird's eye view, you would see it going up over your head. So I've taken a bird's eye view and I've tried to draw it 3D. So in this scenario, if I had asked you what's providing the force on the ball, or draw a free body diagram. So if we go from the side view, if this is my ball, let me stick with blue. So here's a side view. Cut my ball. You would have said, well, I've got gravity pulling down, and I've got tension, so this is F sub W. I've got tension pulling in on the string. Well, it turns out that in this scenario, here, the centripetal force is supplied by tension. So yes, we're talking about something that we haven't talked about before, but tension is a contact force in the electromagnetic category. And remember, this is supposed to be going horizontally over his head. So even though we have centripetal force, it's supplied by tension. Well, before we go down too far down this rabbit hole, we know that force is mass times acceleration. We know that AC is VT squared over R. So the formula for centripetal force is going to be mVT squared over R. So if I wanted to find the tension in this rope, I could use this formula. But the fact that the centripetal force is supplied by other forces leads us to some interesting applications. So let's go to a different color because I'm going to kind of, let's do this guy first. So we have my roulette ball and he's spinning around the roulette wheel. Now there's no string pulling him to the center. So does that mean there's not a centripetal force? No, think about what's the ball in contact with. If in contact with the wood of the roulette wheel? Well, a contact force with a surface is going to be a normal force. So in this example, F sub C is going to be the normal force. And you might say, wait a minute. So if this was my ball and I'm looking at it from the side, I'm still going to have a weight vector. This would be my centripetal force. So I'm saying here, and this is the wall of the roulette wheel. You might be thinking to yourself, but wait, I didn't think normal forces could operate horizontally. I thought they were always vertical. The answer to that is they've been vertical up till now. But no, they can be horizontal. And in this case, it's normal force that's supplying the centripetal force to keep the ball rotating. As soon as we remove that, the ball travels off in a straight line. Well, these two are pretty simple because these are just kind of your everyday forces. Where things really begin to get interesting is when we start to talk about other forces that can supply centripetal force. So let's think first of all in terms of contact forces. What's another contact force that we talked about? Did you say friction? Sometimes friction provides our centripetal force. Let's see if you can think of some examples. Any luck? How about a car on a curve? Friction is what keeps the car from flying off the curve. So friction provides our centripetal force. Well, we know, and I'm going to rewrite this over here, FR is equal to FC. We know that centripetal force formula is mVT squared over R. And we know that friction also has a formula. Let's assume we're talking about static friction. It could be kinetic. We know that the friction force is equal to a coefficient of static or kinetic friction times the normal force. So what we can do is we can fuse these equations into, let's make that kinetic friction. U sub K Fn equals mVT squared over R. And we just basically created a new formula. I call this formula forcing. And this is something that the AP test does. You knew this formula from before. We just learned this formula, and now we can combine them into something completely brand new. What if I have a satellite going around, so let's say we've got a satellite traveling around the Earth. What's our centripetal force? What's supplying our centripetal force there? Pause the video if you need more time to think about it. Did you say gravity? It's the force of gravity. So in this case, I have centripetal force is mVT squared over R. And then on the other side, the force of gravity, let me turn this into an arrow, is Newton's constant, mass 1, mass 2 over distance squared. And this would be the mass of the satellite. So we'll say M1 is the mass of the satellite. Do you notice something interesting? We could actually cancel that out. We don't have to use that, but we'll leave it in there for now. So if I flexed these equations, I could end up with my mass of the satellite times the tangential velocity of the satellite over the radius is going to be gravity m1, m2 over the distance squared. Where did I come up with this? Well, centripetal force and my gravitational force. Gravity is providing the centripetal force, so I can combine these equations. Okay, this is a little bit of a short video, but we're going to launch into sample problems, and I don't want to, that's going to be about another 10 or 15 minutes, so I'm going to split that out into another video. So we'll stop this one for now, and sample problems to follow.